In this lesson, we will solve trigonometric equations and look for solutions on the interval from 0 to 2 pi. Let's start with this one here. 2 sine squared theta minus sine theta minus 1 is equal to 0. If you examine this equation, it almost resembles a quadratic. You have something squared, a linear term, and then a constant. Because of this, I'm going to make a substitution. I'm going to say, let's replace sine of theta with x and see how that changes this equation. By the way, this sine squared, if you square both sides of this equation, on the left you'll have x squared, and on the right you'll have sine squared. So this equation becomes 2x squared minus x minus 1 is equal to 0. This will be helpful because for the time being we'll ignore the sine of theta and solve this equation for x. At the end of this process, we'll put sine theta back in place of x. So how do we solve this thing here, this quadratic? You could use the quadratic formula, perhaps you could complete the square, but I think that we can factor this into two pieces. You'd have to have a 2x and an x. The only numbers that could go at the end would have to be a 1. We just have to decide if they are positive or negative. Because we have a negative middle term, I want to put the negative that will be associated with the larger number. So I'm going to put a negative here, and therefore I'd have to have a positive here if I want this product to be negative 1. You do get 2x squared. You do get negative 1. But if you look at the middle terms, you have a negative 2x and a positive 1x. That definitely adds to a negative x. So we factor the expression, and the reason we're doing this is because we can now set each individual factor equal to 0 and solve for x. So over here, I know I'm going to subtract 1 and divide by 2. If I do that, if you subtract 1, you get 2x equals negative 1. If you divide both sides by 2, you get x is equal to negative 1/2. There's only one step we have to do here. We'll add 1 to both sides, and that is x is equal to 1. Now, that solves this equation for x, but that's what we called sine of theta. Let's now plug that back in and see what we have. I mean, really, where is sine theta equal to negative 1/2? And where is sine of theta equal to 1? If I can find all the angles between 0 and 2 pi where these two equations are true, I will have solved the original equation. Okay, so I've brought in a unit circle as a guide to figure out where these things are true on this interval. So as you start and include 0 and rotate once until you get to 2 pi. I guess this one might be the easier of the two. When is sine of theta equal to 1? Sine is the y value on the circle, and when your y value is 1, you're right here. So this is the spot where sine of theta is equal to 1. And that angle is pi over 2. So this is definitely greater than 0 and less than 2 pi. So this is actually one of our solutions. So I'm going to write it down here. Theta equals pi over 2. That works. Okay. Now there's probably going to be two solutions to this equation. What I'm really thinking of when I try to solve this is, where is sine of theta equal to 1/2? And I know this angle is pi over 6. Now, here's equal to negative 1/2, but all that means is I want to find two quadrants where sine is negative, and we get a reference angle of pi over 6. Sine is negative in the third and the fourth quadrant because sine is the y value. If you want to get a reference angle of pi over 6, you could draw one in here like this. This is pi over 6. And there's one over here like this. Now for this angle here, I know if you rotate to here, you get to pi, which is 6 pi over 6. So if you go pi over 6 more, this is really 7 pi over 6. And we have to represent this angle with something that's bigger than 0 and less than 2 pi. So here is a solution to this equation. Theta is equal to 7 pi over 6. Now there's going to be another one it's very tempting to say, oh, well, if you go backwards pi over 6, you can call this negative pi over 6. It's kind of tempting to say, hey, is that the solution? Negative pi over 6. And the only thing that would be wrong with this is if you call this location negative pi over 6, it does not fall within this interval. So instead of using this, I like to think of it as you're going to 2 pi and you're going backwards pi over 6 from 2 pi. So 2 pi is 12 pi over 6. And if you subtract pi over 6 from that, you get 11 pi over 6. So it turns out there are actually 3 solutions to this equation. We get 7 pi over 6, 11 pi over 6. Those are the places where sine is equal to negative 1/2. But also you have to include this one, pi over 2. That's where sine is equal to 1. This example looks kind of similar to the previous one, except we have a cosine in it, and there's no linear term here. Like, could you still use this trick of, I'll call cosine of theta x and see if it will help me solve this? If we make this substitution and we square both sides of the equation, I see that cosine squared theta is the same thing as x squared. So I'm going to swap that out here in the equation. I'm going to say this is really 4x squared minus 3 is equal to 0. This might not be 100% necessary for the problem, but I think it'll make it look a little bit cleaner. To solve this for x, I'm going to add 3 to both sides. And then I'm going to divide both sides by 4. To solve this for x, we will take the square root of both sides. And if you call x the left, you have to put plus or minus root 3 over 4 on the right. Now, if I put this back in place of x, I get we need to solve the equation where is cosine of theta equal to plus or minus the square root of 3/4. Now the answer we get over here should be something familiar to us if we want to, potentially solve this thing for theta. And 3 over 4 under the square root doesn't look completely familiar, but I think that's because we have to simplify this a little bit. I mean, this is really plus or minus, you can break it up into 2 square roots. That's the square root of 3 over the square root of 4, and the square root of 4 is really 2. So I mean, really the equation I'm looking to solve here is when is cosine of theta equal to the positive square root of 3 over 2? And when is it equal to the negative square root of 3 over 2? So I had to change it a little bit so it looked like something a little bit more familiar, something that we know about sines and cosines. Okay, so where does cosine of theta equal positive root 3 over 2 and negative root 3 over 2? Let's bring in a unit circle as a guide. All right, so for starters, where is cosine equal to positive? I'll put root 3 over 2 like this. So we have to know an angle for which this is true, like something to start with. And it's actually pi over 6, kind of like the last example. It was sine last time, but here with cosine of pi over 6 is root 3 over 2. And actually, that gives me a solution right here. This is the angle of pi over 6. And at this angle, the x value, or cosine, is root 3 over 2. Is there another angle where the x value, or cosine, is also going to be positive root 3 over 2? The places where cosine is positive is in the first quadrant and also the fourth quadrant. So that means we should have an angle down here where cosine is also equal to positive root 3 over 2. And what angle is this? If you go backwards from 2 pi by pi over 6, you get 11 pi over 6. So these are the 2 angles that solve this equation. So that is theta is equal to pi over 6 and 11 pi over 6. But what about where cosine is negative root 3 over 2? So for this here, let's see, the place where cosine is negative is in the second and the third quadrant. So this is where cosine of theta will take on a negative value, and specifically we want negative root 3 over 2. By using symmetry of the circle, I know we're talking about these two angles. So I have to know, like, well, what angle is this and what angle is this? If this is pi radians, or 6 pi over 6, and you go backwards pi over 6, well, this angle has to be 5 pi over 6. So I'll include that here. That's one of my angles. And this one would be, well, if this is 6 pi over 6 and you go pi over 6 more, that's going to be 7 pi over 6. So that means we have two more angles that solves where cosine is equal to negative root 3 over 2. 5 pi over 6 and 7 pi over 6. There are 4 solutions to this equation. So we got pi over 6, 11 pi over 6. That is where cosine is positive. And 5 pi over 6 and 7 pi over 6 is where cosine is negative. In example 3, we now have an equation that has both sines and cosines in it. So what happens if you have like a mix of two different trig functions? I don't know if making a substitution is going to be very useful for this problem, only because everything is to an exponent of 1. But what does jump out at me is between this factor and this factor, there is a cosine that we can factor out. If you have an equation that's equal to 0, sometimes factoring one side can be helpful. So that's my first thought. Let's try it out. What happens if we actually factor out cosine? Well, if you factor it out from here, you're left with a 1. So I'll put 1 plus, and the only thing left here is going to be a 2 sine x. This is great. We have two separate factors, and in each factor, there's only one trig function. So if you set each factor equal to 0, I think we'll be able to solve for x pretty easily. Not much left to do here. Over here, I'm going to subtract 1 and divide both sides by 2. So I know the equation is, well, 2 sine of x has to be negative 1, or sine of x is equal to negative 1/2. We solved this equation already back in example 1, and we saw that the two solutions were in the third and the fourth quadrant. That was 7 pi over 6 and 11 pi over 6. We used pi over 6 as a reference angle, and therefore the places where it's negative are in the third and the fourth quadrant. So you can check that out in example 1. But here, where is cosine equal to 0? Maybe that would be useful to look at a unit circle to help figure that out. All right, so here is our unit circle. Where does cosine take on a value of 0? The coordinates to focus on are from here and here. So this point is 0, 1, and this is 0, negative 1. The x value for these 2 points is 0, and that's the definition of cosine. So the angle here between 0 and 2 pi for this point must be pi over 2. And if you're counting by pi over 2s, that's 1 pi over 2, 2 pi over 2, and 3 pi over 2. So there are two places where cosine equals 0 in the interval from 0 to 2 pi. Pi over 2 and 3 pi over 2. That means overall there are 4 solutions to this equation. Pi over 2, 3 pi over 2, and then also 7 pi over 6, and 11 pi over 6. Here in example 4, kind of like building up to this, we have an equation with both sines and cosines, but now they're not both to the first power. In fact, we have a sine squared in the equation. So because we have this exponent of 2, like it's making me think quadratic, and perhaps, making a substitution like x is equal to sine of theta or x is equal to cosine of theta would be a good move. But, if you try either of these, it kind of like won't work to start with. For example, if x is equal to sine of theta, well, this is going to be x squared, but then, well, what's cosine of theta? Like you still would have cosine in the equation, which is bad. Like you would only want x's. And if you let x equal cosine theta, well, this thing becomes an x, but it doesn't get rid of the sine squared. So it's like, where do you go from here? As equations like this become more complicated, sometimes using a trig identity to simplify it could be helpful. And what would be nice here is there some way where we could either get rid of this sign and replace it with some type of cosine, or same thing here, could we get rid of this cosine and replace it with a sine? So before doing this, I want only sines or cosines in the equation. There is an identity that will be helpful, and that is this. Sine squared of theta plus cosine squared of theta is equal to 1. The reason this is helpful is you can solve it for sine squared of theta. That's equal to 1 minus cosine squared theta. So you can actually take this thing here and replace it with this. Now you have an equation with only cosines in it. Let's write that out. Sine squared of theta is really 1 minus cosine squared theta. I'll just copy down the rest. Minus 6 cosine theta minus 6 is equal to 0. Okay, this equation is equivalent to this one, but this, it only has cosines in it. So what we can do is we can actually use this. I'll use the substitution in here to solve for cosine. All right, the equation becomes 1 minus, so if we square cosine, that's really x squared, minus 6x minus 6 is 0. Okay, if we combine like terms, that's negative x squared minus 6x, positive 1 and negative 6 is minus 5. And there is a negative in every term, so I can divide both sides by negative 1. And what that's going to do is change this to a positive x squared, a positive 6x, a positive 5, and that still is equal to 0. Okay, still the goal is we got to solve this for x. I guess you could use a quadratic formula or completing the square, but I think this factors. Like you have to have an x and an x. Everything's positive, so a plus and a plus, and it looks like the numbers 1 and 5 will do the job. 1 and 5 multiplied to 5. The sum of those two numbers is 6. I now have two factors that can set equal to 0. That is, where is x plus 1 0? Where is x plus 5 0? Well, this one's 0 when x is equal to negative 1, and this one is 0 when x is equal to negative 5. We can now put cosine back in place of x and solve the following equations. When does cosine of theta equal negative 1? When does cosine of theta equal negative 5? All right, maybe we can use a unit circle to help determine the angles that make this true that fall within this interval. So when is cosine of theta equal to negative 1? That has to be referring to this point here. The x-coordinate at this spot is negative 1, and that is the value of cosine. What is this angle? This is pi radians. So if we're solving this equation, where is cosine of theta equal to negative 1? The answer is theta is equal to pi. Well, what about this equation? Where does cosine equal negative 5? On this unit circle, what you're looking for is, is there an x value? Like if we're thinking about this equation here, is there ever an x value on this unit circle that has negative 5 for its value? And the answer is no. Any x value on this circle, the smallest one is negative 1, the largest one is positive 1, and you get everything that's in between, but you never get anything beyond negative 1 or positive 1. So the answer to this is there are no solutions to this equation. Cosine never equals negative 5. In fact, it's never anything less than negative 1. Since there are no solutions from this equation, the only solution to this problem is here, when theta is equal to pi. And that came from where cosine of theta was equal to negative 1. Let's look at one more example here. Another question where we have a mix of sines and cosines, but something slightly different happens here as well. The thing that's different is, okay, here you have a cosine of x, but over here there's a sine of 2x. this is a problem for solving the equation. It'd be nice if they're both either x or if they're both either 2x. Like, you don't want both. You'd like one or the other. And the question is, well, is there a way to deal with this? And I think we'll have to use a trig identity to help us. So I'm seeing this 2x here, and this is making me think there was something called a double angle formula, and we had them for sine, cosine, and tangent. What is the double angle formula for sine? That is there a way to simplify sine of 2x? If you don't remember it, that's okay. You just have to know that there might be some identity that could be helpful here. So I'm just going to look it up on a table, and sine of 2x is actually equal to 2 times sine of x times cosine of x. So this identity is going to move us forward a little bit because, well, we started with a 2x, which we don't want, and if we use the identity over here, well, then we've reduced the 2x down to just x's. So in this equation, I'm going to swap out sine of 2x with this thing. The equation becomes 2 sine x cosine x is equal to negative root 3 cosine of x. So how do we solve this thing? There are a couple of ways to do it. You could add this to the left side, putting a 0 on the right side of your equation. That's pretty much the approach we've used in the previous questions. Let one side equal 0, factor the other side, set each factor equal to 0, and go from there. I want to try something different, a slightly different approach here. I'm seeing there's a cosine of x on both sides of the equation. Can't you just say, well, I can cancel it from both sides, right? And if you do that, you're left with 2 sine of x is equal to negative root 3. And hey, we can solve this equation by dividing 2 to the other side and really solve where sine of x is equal to negative root 3 over 2. And this process is valid, but there is something that you have to be careful about. Anytime that you cancel a factor from both sides of the equation, you have to also check, well, where does that factor equal 0? These are also solutions to this equation. If you think about it, if you put the number 0 here and the number 0 here, that is a solution because the left side is 0 and the right side is 0. If you forgot to check this and you just cancel the cosine, you're only solving this equation and you're ignoring all of these possible solutions. So you have to be careful about this. If you cancel factors from both sides of an equation, you have to include any place where those factors are equal to 0. So we're really solving two equations, this one and this one. But we can solve those. Starting with this one here, maybe I'll bring in a unit circle as a guide to solve these two things. So here's my unit circle. I guess looking at this one first, I believe we've done this already in one of the previous examples. Where does cosine equal 0? We're looking at x coordinates that have a value of 0, and that is at this point and this point. So x is equal 0 to here, and it's equal to 0 here for those 2 points, and the corresponding angles are pi over 2 and 3 pi over 2. So those two angles make this equation true, so they are solutions to this equation as well. But what about this? We also need to include wherever sine of x is equal to negative root 3 over 2. I again like to think of, well, what if it were positive root 3 over 2? Like, what if I was really solving this equation? Do I know an angle that would help me do this? And the angle that works is pi over 3. Of course, that's not a solution to this equation because, well, this is negative and this is positive. So we just want to check quadrants where sine is negative. Sine is negative in the third and the fourth quadrant. So we want to choose two angles that have pi over 3 as a reference angle. There is one here because this is pi over 3. And there's one here because this is pi over 3. So the question is, well, what angle is this and what angle is this? This is 3 pi over 3, right? If you go pi radians, you've gone 3 pi over 3. if you go pi over 3 more, the angle that's down here is 4 pi over 3. And if you keep counting by pi over 3s, this one's going to be 5 pi over 3. So these two angles are definitely within this interval, and they are both solutions to this equation. So that is x is also equal to 4 pi over 3 and 5 pi over 3. There are 4 total solutions to this equation, and it came from solving 2 separate factors equal to 0. I took a slightly different approach. Like I was saying before, it's completely valid to add this to the left side. Then you would factor the left side and set those factors equal to 0. You will arrive at these 2 equations, but I wanted to look at it this way too because it is also valid.